Assalamualaikum. Hi everyone. So this is a video for chapter 5 hydrocarbons. In this video, we're going to discuss the subtopic 5.2 alkenes, and at the end of this lesson, you should be able to first explain the addition reaction of an alkenes by going through these different reactions, and then predict the product form by using the Markovnikov Rule and also the AntiMarkovnikov Rule. After that, we're going to look, explain and predict the reaction of alkenes by going through an oxidative cleavage by ozonolysis and also reaction with hot acidified KM-Pensyarah. And lastly, explain the unsaturation test for the alkenes by using Bayes test, bromine in dichloromethane and also bromine water. Reaction in alkenes. So, for the reaction in alkenes, we're going to look on two different types of reaction. The first one, we're going to look on the electrophilic addition reaction, and the other one, we're going to look on the oxidation reaction and also oxidative cleavage. So, let's start with the first one. Electrophilic addition reaction. So, in this electrophilic addition reaction of alkene, we have 6 different reactions. So now let's take a look one by one. So this is our alkene. So as you know, the functional group of alkene is carbon-carbon double bond. And we know that at the carbon-carbon double bond, the electron density is very high. So that's why the reaction will start from here. So this is our nucleophilic site. So our alkene itself is a nucleophile. So reaction will occur here where we're going to add another 2 atoms on the carbon at the carbon-carbon double bond. So I'm going to label the atom over here. So the carbon as carbon number 1 and carbon number 2. Okay, so we're going to add our reagents at carbon number 1 and carbon number 2. So this nucleophilic site, this nucleophile will attack the electrophile. So that's why the type of reaction for alkenes is electrophilic addition reaction. So let's start with the first one. So the first reaction is hydrogenation. Okay, so for hydrogenation, what are the reagents? So the reagent used is hydrogen with platinum. So reagent is hydrogen. Platinum here, it will act as a catalyst, okay, to speed up the reaction. Okay, so at the carbon-carbon double bond, we are adding the hydrogen atom. So hydrogen is the one that is added to the carbon-carbon double bond at carbon number 1 and carbon number 2. So let me just label this. So this is your carbon number 1, carbon number 2 over here. So let me continue. So hydrogen is added. Hydrogen over here is our electrophile added into the carbon-carbon double bond. So besides platinum, we can also use palladium, Pd, and also nickel as the catalyst for the hydrogenation reaction. Okay, so this will be the first reaction. The second reaction, we're going to have halogenation in inert solvent. The reagent that will be used for this halogenation process is bromine and CH2Cl. So CH2Cl over here, or the name is dichloromethane. This is our inert solvent. So basically, it's an organic solvent. So we are adding to our carbon-carbon double bond our halogen over here. So at each carbon-carbon double bond at carbon 1 and also carbon 2 will receive 1 bromine. So this will be the product of your halogenation. So at carbon number 1, it received 1 bromine, and at carbon number 2 also received another bromine. So this will be the second reaction. Next, The third reaction is halogenation as well, but in water. So water is a polar solvent. Okay, so the reagent that will be used for this reaction, since it's halogenation, so you can use any halogen. It's not necessarily you need to use bromine. You can also use chlorine in this reaction. So I just pick bromine as my halogen. So this bromine is dissolved in water. So once the reaction dissolves in water, the product will be slightly different than the one that we have for halogenation in inert solvent. Okay, so the one that we are adding into our carbon-carbon double bond over here, instead of 2 bromine, we're going to add 1 bromine atom and the other one is hydroxyl group. Okay, so how are we going to write down the product? Okay, we're going to write down the product, okay, the position of the hydroxyl group and also the bromine by using the Markovnikov rule. So, what is Markovnikov rule? So, Markovnikov rule states that in addition of HX to an alkene, hydrogen atoms adds to the carbon atom of the double bond that already has greater number of hydrogen atoms. So, to make it simple, this is our alkene. So, from our alkene over here, okay, focus at the carbon-carbon double bond. So, this is carbon number 1, okay, and then this is carbon number 2. Okay, we are adding HX. So, H and also X. Okay, so based on this statement for Markovnikov rule, we need to add hydrogen first. So, the hydrogen will be added to the carbon atom which has more number of hydrogen. So, carbon 1 and carbon 2. The one with more hydrogen atoms is carbon 1. So, that's why the hydrogen atom will be added to carbon 1. Thus, X over here, which is your halogen, will be added to carbon number 2. And this will be the product. Okay, so this is if you are adding H and X. Okay, alkyl halide. But from the one that we did just now, okay, the one that we are adding is bromine in water. So we are trying to add bromine and also OH. So we don't have hydrogen over here. So if we don't have hydrogen, how are we going to know which atom going to be at the first carbon? Okay, which atom going to be here? Which one going to be here? So bromine and hydroxyl group, we will determine based on the priority of the functional group. So these two are functional groups. So the higher the priority, okay, we will not choose for carbon 1. So in other words, if it has lower priority, it will go to carbon 1. It will go to the carbon with more hydrogens. So between bromine and hydroxyl group is a higher priority functional group, while bromine is a lower priority functional group. So that's why if we were to draw, okay, so CH3, CH double bond, CH2. Okay, so this is carbon 1, so this is carbon 2. So at carbon number 1 over here, the one that will be bonded to first carbon is bromine. Why? Bromine has lower priority, so it will go to the carbon with more hydrogen group. So the hydroxyl group will be attached over here. Okay, so this one is applied if you don't have H and X. You have bromine and hydroxyl group, or you have hydroxyl group and chlorine. Okay, meaning when you have two functional group, like I mentioned just now, determine its priority. Hydroxyl group will always have higher priority, the other one will have lower. So the lower priority goes to the carbon with more hydrogens. Thus, hydroxyl group to the other carbon. Okay, so now let's proceed. So, like I mentioned just now, the one that we want to add into our alkene for halogenation in water is actually bromine and also OH. Okay, so by right, this is just a general formula, so bromine and OH. But if you have a real compound, so you need to determine based on the Markovnikov rule. So this is reaction number 3. Now, we have reaction number 4, hydrohalogenation. So by the name itself, hydro meaning we are adding hydrogen. Halogenation, we are adding X, meaning our halogen, either bromine or chlorine. So for this example, I'm adding HCl. So HCl over here is actually an aqueous solution. Okay, so aqueous. So HCl aqueous, so the hydrogen will, to put the hydrogen, we're going to add the hydrogen first. Okay, which rule are we going to follow? The Markovnikov rule just now. The hydrogen will go to the carbon with more hydrogen, while the chlorine will go to the next carbon. Okay, so this is just a general one. When you have a real compound, so you need to follow accordingly. Next, another hydrohalogenation reaction for the 5th reaction. But for this one, the reactant is different. It's a combination of HBr and peroxide. So if you see ROOR, okay, R here is your alkyl group. So meaning carbon bonded to oxygen and oxygen to oxygen, okay, and then bonded to another alkyl group. So this is what we call as a peroxide. So this peroxide, usually we're going to see in the form of H2O2, hydrogen peroxide, or here dimethyl peroxide over here. So why is this combination of reagent is special? HBr with peroxide. Okay, when adding HBr with peroxide into the alkene, the one that we're going to add is H and also Br. We're going to add it into the carbon-carbon double bond, but it will follow AntiMarkovnikov rule. Okay, so what does AntiMarkovnikov rule says? So, for AntiMarkovnikov rule, like I mentioned before, it only occurs when HBr is used in presence of peroxide. So what will happen? The hydrogen atom will attach to carbon with fewer hydrogen atoms. So what does it mean? So if I have my alkene over here, so I will use the blue color one to show you for the Markovnikov rule. So we are adding hydrogen and bromine. So if I were to add HBr, okay, into the carbon-carbon double bond, hydrogen and bromine, if following Markovnikov rule, so I have over here carbon 1, carbon 2. The hydrogen will be added to carbon number 1 and bromine will be added to carbon number 2. So this is true if it follows Markovnikov rule. But once the reaction occurs in peroxide, meaning you have peroxide over here, HBr in peroxide, so this is not valid. Okay, so what will happen is the other way around will occur. So the hydrogen over here, instead of going to carbon number 1, it will go to the carbon with fewer hydrogen, which is carbon number 2. So hydrogen will be bonded here, and automatically our bromine will be bonded at carbon number 1 with more hydrogens. So this will be your product. And like I mentioned before, it's only for HBr in the presence of peroxide. So if, let's say, you have only HBr, okay, HBr without the peroxide over here, so the reaction will follow Markovnikov rule. But if it's HBr with peroxide, it will follow AntiMarkovnikov rule. Okay, So now let's proceed. Okay, so this is just to complete the mind map over here. So like I mentioned before, if you have a real structure, so you need to be aware of the location of the carbon with more hydrogens to put your hydrogen and also your bromine over here. Okay, next. We have here the sixth equation, the sixth reaction as hydration. So, hydration, hydrate, we are adding water. Okay, adding water into our reaction. And this water, it must be in acidic medium. So, that's why it must be H2O in the presence of H3O plus over here. Or sometimes, it is also stated or also written as H2O and then H plus. Okay, but both must be present. Okay, so what are we actually adding into the carbon-carbon double bond? So when we do hydration of alkene, we are trying to add hydrogen and also, okay, I'm just writing down the atom. We are adding hydrogen and also OH over here to the carbon-carbon double bond. So for this one, what rule are we going to follow? Yes, we're going to follow the Markovnikov Rule. So for the Markovnikov Rule, okay, carbon 1, carbon 2. So this, for this example, is not really valid because my alkene is not complete. But if you were to add hydrogen and hydroxyl group to the carbon-carbon double bond, so priority is the same. So hydrogen will have lower priority, hydroxyl group will have higher priority. So with that in mind, the hydrogen will go to the carbon with more hydrogen atoms and hydroxyl group will go to the other way around. Okay, so that will be the product. Okay, and then lastly, okay, so these are the 6 reactions. So next, what I'm going to show you is the test. Okay, like I mentioned before, in the learning outcome, we have unsaturation test. Okay, to determine that the compound is a carbon-carbon double bond. So from this reaction, we have 2 tests actually. So the first one is here. Okay, we have bromine test in inert solvent. So this reaction, the halogenation in inert solvent, is also called as the bromine test. Okay, to show that the compound that we have is an alkene. So when we have a chemical test, it must come with an observation. So what observation are we going to see when we add bromine in inert solvent to an alkene? So observation is the reddish brown color of bromine will decolorize. So remember, it's only for bromine because bromine has a reddish brown color. So we can observe the color change. So that's one. And then we also have another bromine test in water. Meaning for this one, so the 2 halogenation reactions can be our test for the carbon-carbon double bond over here. So the observation will be the same. So if we have a carbon-carbon double bond, when we add bromine in water, the observation that we will get is the reddish brown color of bromine will decolorize. We will not write down become colorless. Okay, instead we are using decolorize to show that the color is changing. Okay, why don't we use it become colorless? Because sometimes it won't be colorless. There may be some traces of color, but what we can clearly see that the bromine color will change. So instead of being colorless, we state as decolorize. So if you put colorless, is it accepted? No. So it must be decolorized only. Now, the next reaction that can occur in our alkene is oxidation process. And for this oxidation process, you will have 3 different reactions. So let's start one by one. So this is our alkene, the carbon-carbon double bond. So the reaction will occur at the carbon-carbon double bond. So the type of reaction over here is oxidation reaction. Okay, why and how does it differ from the previous reaction, which is electrophilic addition reaction? So let's look at the first one. The first reaction that we have is ozonolysis. Okay, so for ozonolysis, the reagent that we're going to use is ozone first. Okay, we will react it with ozone, and then the second step, we will add zinc in water into the mixture. So when you are writing down the equation, it must be two-step reaction like this. So at your arrow, you write one Roman over here, ozone, and then second Roman, zinc, H2O. Compulsory, it must be like this. Or sometimes, this one can also be written as this. The ozone is the same, but the second reagent, we change it to CH3-2S. Okay, so it will give you the same product, okay, the same reaction, which is ozonolysis. So what will be the product for ozonolysis over here? Okay, so for ozonolysis, we have over here oxidative cleavage. Okay, it's an oxidation reaction. Then, for oxidation reaction, why do we have cleavage over here? Because at the carbon-carbon double bond, what will happen is we're going to break this carbon-carbon double bond. Okay, and then we will have two separate molecules. So now, let's look at the product of ozonolysis. So, when we have an oxidative cleavage based on ozonolysis reaction, it will produce an aldehyde and or ketone. Meaning the product, we will have two products. It's either we'll have an aldehyde with another aldehyde, or we have a ketone with another ketone, or we have a mixture of aldehyde and also ketone. But you will have two different compounds. So, let's say this is our alkene. Okay, so I have over here carbon-carbon double bond, first carbon over here. Okay, so this first carbon, and then this is the second carbon. So for the first carbon, it is bonded to two alkyl group, and the second carbon is only bonded to one alkyl group. So we react this carbon with ozone for the first step, and then we add zinc and water. So the product that you will get first, you will get a ketone. Okay, how do I know we will get a ketone? So basically, since it is an oxidative cleavage, what will happen here is at the carbon-carbon double bond, we will separate this bond. So you will get a separate molecule. So this is actually carbon number 1. And then another one, we will have ketone, and this is actually carbon number 2 that has been separated. So at the point where the separation occurs, at the point where the bond breaking occur, we add a bond, we add carbon double bond O. So the oxidation occurs here. As you know, oxidation, we have increase in number of oxygen. So at the point we break, so you will get a carbon-carbon double bond, and also this one. Okay, so the product, one will be ketone and the other one will be aldehyde. Why? Because carbon number 1 over here is bonded to two alkyl group. So the carbonyl group is in between two alkyl groups, so that's why we have a ketone. So if over here, the carbon bonded to oxygen over here, the carbonyl group is only bonded to one alkyl group. Okay, and then one hydrogen. So this is the structure for aldehyde. Okay, so like I mentioned before, must you get a ketone and aldehyde for the product? Not necessarily. So if, let's say, okay, you have your alkene like this. Okay, H, 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 and H. So this is your alkene. And then undergo ozonolysis, so this bond will break. So this is carbon number 1, this is carbon number 2. So you draw back exactly the same thing that you have from carbon number 1, and at the carbon you put double bond O. So what is the product that you get over here? Okay, so since it is not bonded to any alkyl group, so this is your aldehyde. Okay, and then what happened to the second one over here? So it will be the same thing, carbon, okay, H and H. And then at the point where the bond breaks, you put double bond O. So you will also get an aldehyde over here. In fact, you get the same aldehyde. So for this one, okay, this is your ethene. For the ozonolysis of your ethene, you will get the same aldehyde. So same goes if over here, okay, instead of hydrogen, I put, okay, CH3, 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 and then CH2, CH2, CH3. Okay, so CH3. Okay, so CH3 over here. So the bond will break over here, ozonolysis. So this is carbon number 1, this is carbon number 2. So what will be your product? So at carbon number 1, so I use green color. At carbon number 1, it is bonded to CH3 and then CH2, CH3. Okay, so you get what I mean. So at the point where it breaks, it will become carbon double bonded O. So since over here you have two alkyl group, so you will get a ketone for carbon number 1. Same goes for carbon number 2. So at carbon number 2, okay, it is bonded to CH3 and then another CH3. So at the point where it breaks, it is double bonded to O. So this is actually your carbon number 2. So as you can see over here, this structure also bonded to two alkyl groups. So you get a ketone. So you get here a mixture of ketones. So the product over here will be determined by what substituent you have here. Okay. Okay, so this is the summary of what I just said just now. If there's no hydrogen attached to the carbon-carbon double bond, like this one, okay, so it will be a ketone. But if you have at least one hydrogen attached to the carbon-carbon double bond, the product will be aldehyde. So now, let's complete this mind map. Okay, so this will be the product just now, aldehyde or ketone. So, next is reaction of alkene with hot acidified KM-4. So, for hot acidified KM-4, it will be written like this. KM-4, acidified, you must put down H3O+, and then to show that it is hot, put the heat symbol over here, the triangle, to show that it is heated. So for this one, the reaction that will occur, or okay, before that, this one, sometimes it can also be written like this. KM-4, OH minus, and then heat. So two-step reaction. And then the second step, only it is acidified. Okay, but mostly it will be written like this. But there will be some reaction, it will write down as this one. So, for reaction with hot acidified KM-4, this is also an oxidation reaction. Okay, so the type of oxidation over here, we will also have an oxidative cleavage. So, in other words, what does it mean when we have an oxidative cleavage? So, the carbon-carbon double bond over here will be breakdown. Okay, we will break those carbon-carbon double bond and we will get two different products. So now, let's take a look on what is the product for oxidative cleavage with hot acidified KM-4. So reaction with hot acidified potassium permanganate. So it will produce ketone and or carboxylic acid or carbon dioxide and water. Okay. So let's look at the example over here. So I have over here my alkene. Okay. So let me label this. So this is carbon number 1. This is carbon number 2. Okay, carbon number 2 over here. So when we did the oxidative cleavage, okay, when we put hot acidified KMnO4, the bond over here will be break. Okay, so the product that you might get is ketone and also carboxylic acid. Okay, why do we get carboxylic acid over here? Okay, so if there's no hydrogen attached to the carbon-carbon double bond, so automatically you will get a ketone. At the site where the bond breaks, we will introduce carbon double bond O. So that carbon double bond O, okay, it has 2 alkyl group. The carbonyl is in between 2 alkyl group, so it's a ketone. Okay, but what happened at carbon number 2? So this is carbon number 1. This is actually your carbon number 2. So for carbon number 2, when you have 1 hydrogen attached to the carbon-carbon double bond, it will become carboxylic acid. Okay, why? So actually, the process that occur over here, okay, so we're going to focus on this one. So when the bond break, okay, you will get a carbon-carbon double bond over here. So R and then H. Okay, at first, we will get an aldehyde. Okay, but hot acidified KMnO4, we can say that this is a strong oxidizing agent. Okay, so in the presence of strong oxidizing agent, our aldehyde will be further oxidized. Okay, at which part it is being oxidized? The hydrogen over here. Okay, because you know oxidation, we're going to increase the number of oxygen and we're going to remove hydrogen. So the hydrogen over here will be further oxidized and will be substituted. So this is the alkyl group. So the hydrogen will be substituted with OH. So that's why for aldehyde, okay, for a carbon that is bonded to 1 hydrogen, it will straight away get your carboxylic acid. So this is what happened at carbon number 2. Okay, so in exam, do you write this one or this one? Write down the final product, meaning the carboxylic acid. So if you get a hydrogen over here, you straight away will see that it is for carboxylic acid, okay, not an aldehyde. Okay, for this one, if 2 hydrogen attach to carbon-carbon double bond, the product will be carbon dioxide and water. Okay, so what does this mean? So for example, I have this. Okay, so carbon-carbon double bond. Okay, hydrogen, hydrogen. Okay, this is hydrogen. This is CH3. So I react this with KMnO4. Okay, hot acidified KMnO4. So as you know, the bond over here will break. So I have carbon number 1, I have carbon number 2. So at carbon number 1, CH, CH3. Okay, so like I mentioned before, double bond O. So you have over here is your aldehyde. So what you need to do, change the hydrogen over here, change it to hydroxyl group. So you will get your carboxylic acid. Now, this is for carbon number 1. Okay, this is carbon 1. Okay, plus, so what happened at carbon number 2? So at carbon number 2, CH and H. So you will have double bond O over here. So the one that we have over here is methanol. So once you have methanol, it has 2 more hydrogens over here. So this hydrogen will be further oxidized. So instead of getting a carboxylic acid, this one, okay, will straight away produce carbon dioxide and H2O. Okay, so I hope this is clear. Okay, so now let's move on. So let's complete the mind map. So the product just now, like we discussed, it will be either carboxylic acid or ketone or mixture of both. Okay, now the last reaction for oxidation of alkene is reaction with cold dilute KM-4. So this third reaction is slightly different from these two. Okay, why does it different? For ozonolysis and reaction with hot acidified KM-4, we have oxidative cleavage where at the carbon-carbon double bond, we break those two bonds to form two separate molecules. Okay, but in reaction with cold dilute KM-4, there will be no bond breaking at the carbon-carbon double bond over here. Okay, so on the arrow, we are going to write down KM-4 dilute OH minus and also cold. So you need to mention the word cold over here. So the product that we will get here actually, it looks like an addition reaction. So we are actually adding at the carbon-carbon double bond the hydroxyl group. But we did not put this as an addition reaction because it's actually not adding. If we add something, it must come from another substance. But here, we don't have a second substance. Okay, it's just the rearrangement from the hydroxyl group. The hydroxyl group over here will be added into the carbon. So instead of addition, we classify this as an oxidation reaction. Okay, the difference between these two, the bond, the carbon-carbon bond over here is not totally broken. Okay, the carbon-carbon bond will not be separated. Okay, it still have one single bond over here. And at each carbon, we're going to put OH. Okay, and the side product over here is MnO2, manganese oxide. And there's an arrow going downwards over here. So if you see this arrow, what does it mean? It means that MnO4, manganese oxide over here, is solid, or we call it as precipitate. Okay, so do you need to show the arrow in your equation? Yes, you need to show the arrow. So the reaction over here for reaction with cold dilute KM-4 is actually your Bayes test. So for Bayes test, okay, it's another test to show the unsaturated carbon-carbon double bond over here. So the observation that we will get from this reaction is the purple color of KM-4 will decolorize, and at the same time a brown precipitate will form. So our manganese oxide over here is our brown precipitate. Okay, so that will be the reaction in alkenes for oxidation reaction. So remember, we have ozonolysis and reaction with hot acidified KM-4 where we have an oxidative cleavage. And lastly, we have a reaction with cold dilute KM-4, a normal oxidation reaction that will give us a precipitate of brown color manganese oxide. Now, we're going to work backwards. Okay, we want to identify the position of double bond from the product of your oxidative cleavage. Okay, so just now we did oxidative cleavage and we get a product aldehyde, ketone, or ketone and carboxylic acid. So if we are given the product, how do we determine where the position of carbon-carbon double bond in the alkene? So let's take a look one by one. So the first one, identify position of double bond from the product of ozonolysis, meaning from our ketone and aldehyde. So let's say this is our oxidation product. So over here, okay, we have a ketone. Okay, so this is ketone. And then over here, we have an aldehyde. Okay, so we want to draw the alkene. Okay, so you need to focus on where the position of the carbon double bond, or where is the position of the carbonyl group. So this is the position of the carbonyl group, and this is the position of the carbonyl group. So label this carbon. So what do I mean by this? So let's say in this ketone, I labeled it as number 1, and then this ketone as number 2. Okay, so what you're going to do is join these two carbon to deduce the starting material. So you will first, okay, so this will be the product. So what you did actually, this is carbon number 1 and this is carbon number 2. Number 1 from the ketone and number 2 from the aldehyde. So what you do is you form a bond between these two carbon. Okay, and then everything else, write it the same. Okay, so what do I mean by this? So if you look over here at carbon number 1, okay, it has an alkyl group, methyl group, and also an ethyl group. So at the carbon number 1 over here, after drawing the double bond with carbon number 2, at carbon number 1, it has methyl, so draw the methyl, and then it has ethyl, so draw the ethyl. The position can be exchangeable. What do I mean by that? You can also write CH2, CH3, CH3 like this. Okay, so this is carbon number 1. So it is also accepted. Okay, it's the same. It's just meaning the two alkyl group is still bonded to the same carbon over here. Okay, and then carbon-carbon double bond. So at the second carbon, so the second carbon over here, it's bonded to one hydrogen, and then we have over here a butyl group. So you have 4 carbon. So that's why at the second carbon, this is the second carbon over here, it is bonded to hydrogen and also CH2, 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 CH3. So this is how you draw your alkene from ketone and aldehyde, the product of ozonolysis. Okay, now let's look at another one. Oh, sorry. The name of this compound is 3-methyl-3-octene. So you can try naming yourself. So the next one is identify the position of double bond, okay, from the product of reaction with hot acidified KM-NO4. So from hot acidified KM-NO4, so this is the product for the oxidation of alkene by using hot acidified KM-NO4. So what is the product that you will have over here? So here you have carboxylic acid. Okay, so I just put as Ca, carboxylic acid, because you have over here C double bond O OH, and here you will have your ketone. Okay, so label the carbon. So this is carbon number 1, okay, and then this is carbon number 2. Okay, so we will join these two carbon. So this will be the site where we're going to join these two carbon to deduce the starting material. So what are we going to get? So this will be the structure. So if you can see over here, okay, so this is carbon 1, okay, and then this is carbon 2. Okay, carbon 1 and carbon 2, my 1 is gone. Okay, so that is carbon number 1. So if you look at your carbon number 1 over here, what do we have? Okay, since it's a carboxylic acid, so 1 alkyl group over here, and the OH is changed to hydrogen. So that's why you have 1 alkyl group CH3, CH2 for carbon number 1, and also 1 hydrogen over here. And For the ketone, it is very obvious. This ketone is bonded to one methyl group and then one butyl group over here. So that's why one methyl, one butyl. Okay, so try deducing the name of this compound. So the name is 4-methyl-3-octene. So that is our discussion on all the reaction of alkenes, which we have. First one is the electrophilic addition reaction, and then the second one, oxidation reaction. Okay, and then lastly, we discuss on how to deduce the structure of your alkene from the product of oxidative cleavage. So if you have any problem, we can further discuss this in our class. Okay, so with that, thank you for listening until the end. Goodbye everyone.